Yo, what's up guys, welcome to another video of this channel. The time has come. The first of the 3 final bosses was uploaded, challenge 7, check it out. Today we're going to jump to challenge 8 of FlareOn and see what we get. So this will be a tough one again. It will need some a lot of troubleshooting and debugging, because as always I'm going to showcase the entire learning process, not jump the hard parts and present you, wow, it works. I want you to see the entire process of thinking and the logical deduction to come to a conclusion. Of course it takes time, so if you are really interested in learning, you should be okay with that. I'm kinda aware that lately basically the attention span of people has dropped significantly due to short form content of short form, like reels, like stories, TikTok, Instagram, etc. So I think and based on my statistics from the YouTube channel, the average view duration is like 4 minutes, 4 or 5 minutes, and I'm pretty sad with that. So I think after 8 and 9 this will be the last videos I'm doing of this form, like really long form, to show the entire process, because I don't think there is any meaning on that. I mean, I enjoy it, but if really no one watches it, it means two things: either they can't focus for so long, so yeah, maybe I should start editing those 6 hours video, but I won't do it. I won't edit a 6 hour video and then render it on my shitty machine. Or they find them boring, in which case today there will be some trance music playing on the background, and by the way, I'm gonna have a disclaimer on this. So in this case, when there are some moments of silence and I don't talk, again they will hear some music, and that's something that's kind of better off than hearing anything. Yeah, this is how it goes. So let's jump ahead and see challenge 8. So about the music, by the way, before disclaimer, if you have any feedback on these videos, or if you find them boring, don't it's not that bad to say I won't be disappointed to something, because I honestly enjoy feedback and I like it, because it honestly makes me better, and all of us will learn through feedback and mistakes, etc. I mean, I'm doing these videos because as a viewer, as someone who wants to learn, I would watch these videos, like not maybe 6 hours, but 2-3 hours certainly, because yeah, it's my life motto from now on, and this is something basically that reverse engineering has taught me, that first of all, you don't really learn anything if you don't practice hands-on with it. No matter how many books you read, no matter how good you are in theory, if you haven't gotten your hands dirty, you don't honestly learn. Knowledge does not get into your brain. It's just things you have learned by heart from the book, right? Yeah. And what was my other life motto? Yeah, basically that we cannot, it's I find it hypocritic a bit to hide, if we want to learn someone something and we hide from him the process of struggling and being in pain, and then come to a result. Or if you don't come to a result, just ask for help, but when you are desperate. This is my point of view in anything from now on, and this is how reverse engineering taught me to do so. You basically struggle, sometimes reinvent the wheel, but if this is what it means to learn for you and works better for you, then this is what you should do. You should always follow your your heart and mind on these things. So if you don't struggle a lot and you don't find something painful, the moment you find something painful and keep and being stubborn and keep hitting it until you solve it, or until you find it, or anything, this is where true experience lies. This is the lesson taught by reverse engineering, and works pretty well in life as well. I think, for me, I don't know. This is all personal, of course. So, a disclaimer: I do not own any kind of this music. I just love this channel. I have subscribed also. So if you are the creator of this channel, or Ferry Corsten himself, or Cosmic Gate, I don't know, I'm gonna play some more musical afterwards. I do not own any of this. I do not make these videos for financial purposes. I don't want to earn any money from this. It's purely for educational purposes. So yeah, don't ban me, okay? I do not make any money from this channel, honestly. I have no ads, I get no money. I'm just doing it purely for educational purposes. So let me play these gems, please. Okay, so jumping onto the challenge 8. It's called FlareAuthenticator. Okay, let's jump into it. The password, as always, is Flare, and let's open it. So we are presented with a few DLL files. I think it's pretty loud. Fuck. Yeah, maybe that's better. Okay, so we're presenting with some DLL files and a batch file and the exe. So this means that this binary is not statically linked. What does static link means? It means that instead of having all these DLLs in a separate directory as a separate file, static linking means that all this code from these DLLs is embedded into one single binary. So this removes the dependency of these DLLs. All the code is just built inside. So there is no reason to have any dependencies, any third-party dependencies. I actually want to like that. Awesome. So it looks like this is a Qt application. What is Qt application? So the development framework for graphical user interface. Yeah, Qt software. Yeah, so this is a library, a C++ library. What's the best way to explain? Yeah, it's a framework basically that you can write web applications with a graphical user interface. Of course, it's written in C++, and because this is a Qt application, for some reason we cannot just simply open this up like that. It says you need to execute run.bat instead. We will see on the reversing process why this comes up. So this batch file is pretty simple. It just sets an environment variable for this specific environment, because when you have a bat file and you set an environment variable there, Then after this script terminates, the environment variable does not exist anymore. So it basically executes the binary FlareAuthenticator through the bat file, because in this environment there is this specific environment variable. So let's execute run.bat, and this is a classical find the password style challenge. So we can type pretty much anything here. We can delete. I'm writing through the keyboard now, so they have enabled also keyboard shortcuts, keyboard pads, sorry. Backspace works as well instead of deleting, and when you finish with your password, you just click OK and you get wrong password. The task is to make this pop-up say correct password. Okay, this is pretty much it. This is the idea of the challenge, pretty simple. So let's jump to a PBear and see a few things, not that required, but okay. So so jump to the resources. There's nothing interesting by default. These are the default ones. So from the Qt library you can see that there are a lot of functions, and it would be very annoying if it was statically linked, because all of these functions would be embedded inside the binary, and fingers crossed, thank God, pray that we had symbols. If we didn't have symbols, and all these functions were statically linked, then bad news. Okay, so okay, a classical binary. The text segment is decent, quite large I would say, so there might be some obfuscation, but we will see. Our data section is also a bit large, I can say. Yeah, so resize to fit sections. No resizing, okay. So let's open this binary to IDA. Okay, let's open this up, and while this loads, let me show you something, a cool trick. So sorry, then let's open PBear again. Let me see, is it loading? Okay, let me get the volume of IDA a bit down. Okay, so let's jump to PBear. I go to the optional header, and please look at the image base. Can you see this number? This is this number, 140 million. Okay, so this is the image base of the binary. So if you see at the assembly, let me jump to the top of the text section, you see that the virtual address of the text segment is on 140 million and 1000. So the image base is 140 million, the text segment is 140 million plus 1000 in hex. If you see here, you can see that the virtual address of the text segment is indeed 1000. We can jump to so we can jump to this offset. Hopefully this jumps actually, and you can see that this is the start of the R data section. So this is IDA basically shows virtual addresses, not raw addresses. To find the raw addresses, you open this in disk, from the disk. So you open it, you literally open the raw bytes of the binary, and you see that the raw address is 400 instead of 1000. And you see that indeed on the raw offset 400, you see the start of the text segment. If we jump to 8DA00, this is the start of the R data segment, etc. and so on. Yeah. So remember, okay, so let's, of course we're going to debug this binary at some point. So let me put a playlist now. This one I liked it kinda. Is it low? Okay. Okay, so if we attempt to just drag and drop in x64dbg, of course we're going to get an error. So, but the problem is that we cannot execute a bat file in x64dbg. We're going to get an error. So what can we do? We can edit the run.bat file, and instead of starting the FlareAuthenticator binary, we can start instead x64dbg and give it the binary as an input. This is a good trick actually. So let's get the path of x64dbg. This is it. So it's x64dbg.exe. So we basically start this exe and pass it as argument FlareAuthenticator. So let's close this up and run the bat file. You can see that the debugger is opening correctly. I think I have some breakpoints left here as well, sorry. Let me remove all the comments. Actually, you know what? I don't know, should I keep the symbols, the rename things or not? Okay, I'm just gonna remove some things. Please bring this era of trance music back, please. This is true trance music, honestly. Okay, hopefully we don't get much spoils from the current labels, but what can we do after all? So let's jump to the program main. What's the entry point? Let's see the entry point. So the entry point is 8D to 8C. So let's jump to FlareAuthenticator plus this offset. Oh, this is actually the... Is this it? Is this... What? Oh, this is the main. So this is the main function. How did I figure out? Yeah, this is classical initialization stuff. Then it jumps to the main loader. If we run through these functions, okay, I have renamed the symbol, of course. I knew that, but even if you don't know, you can see the arguments being loaded here and passed as an argument to this function. So you actually know this is the main function. If you don't know, you can just press F8. Okay, fuck. Let's refresh and show you how I figured it out. So you pass these checks. If I press F8 now, the app starts. So you know this is the main function. Okay, and let's rename it to main. Let's rerun and press F9. Then we are into main, and already we can see some pretty weird stuff happening. A lot of call RAX things, a lot of constants being loaded, shift right, multiplications, divisions, a lot of things, which pretty much seems like an obfuscation to me. If we open main here, you can see that the main function actually looks like this, and this is terrifying. You see that there is really a lot of code here. Yeah. So we won't have any luck debugging step by step through this. This is gonna be tough. But let's focus on something else. Check the real address of main. So the address of main is 140 million and plus 74,860. But look at the address of main here. It's completely different, and that's because the image base is different here. So it turns out that this binary has ASLR enabled, so each time it gets loaded into, each time it runs, it gets loaded to a different base address. And that's basically how, yes, this is basically what ASLR is. It randomizes, what does ASLR mean? I don't remember the address space layout randomization. In a security feature, it works by scrambling the memory locations used each time the system boots. Yeah, this is because you don't want to have static memory addresses inside your binary to prevent attacks. Okay, so this binary has ASLR enabled, so it's loaded into this address. If I close 64dbg or remove the binary and try importing it again, it will have another address here. So since this is different, this address is, the address of main is also different. But you can see that the RVA, the relative virtual address, so this plus 474, this thing is basically the same. This doesn't change. This is 74,860. You can see that this is called the RVA. This is the relative virtual address, and it's relative to the base address. So the base address is this thing until db and zeros, and the relative virtual address is plus 74,860. So in IDA we can go ahead and rebase the program. This is the current base address, so we can change it to the base address of this, sorry, 7f f7 1db0 1db 5 zeros. Yeah, okay, we can go ahead. I won't do it because it will take time again to relocate everything, so we can go ahead and do this. Then we're going to have exactly the same addresses as the debugger, but this is not a good solution. Instead, we can keep IDA as is because it's easy to work with these addresses. These are more clean addresses. These are much uglier, and let's actually research about this problem. So x64dbg different address PE. So yeah, of course I have already looked after it, but this post will appear to you too, and this guy here has the exact same issue as me. He basically shows GIDR addresses which are like that, but inside the debugger the address becomes this, and there's a perfect solution described here. Actually, the second step is what I'm going to show you right now. You can jump to the pbear and remove this flag, image DLL characteristics dynamic base attribute from optional header.dll characteristics. So this is what are we going to do. So let's open pbear and find these DLL characteristics things. You can see that this is the value of this flag. This is 8160, and there are these flags being set. So this flag is about high entropy 64-bit virtual address space. This flag is DLL can move, and basically this is what we need to change. You see, we need to change the 40 flag to remove it. Image NX compatible and terminal server aware. I don't know what this is. I think this is about, I think image is NX compatible. NX is a security flag in binaries that prevent executing code in the stack of the program. So we can go ahead and see how this 8160 value is constructed. So the flags usually, when you have multiple flags, they are usually combined together with OR, right? So let's make an OR of all of these flags. This is the value 33,120 in decimal. Let's convert this to hex and you see that it's 8160. Make sense? So we don't want the 40, the value of 0x40, which is 64. Yeah, we just we don't need 40, so let's get rid of this. So we have this value, it's 8120. So let's just patch this out. Let's close the debugger first, and let's patch this out to 81 and 20. And you see that the flag is magically disappeared. If you then open the debugger, run. Oh, of course, sorry, it won't run. Sorry, yeah, I haven't saved the binary changes yet. I need to save this. Right. So let's save the executable. Let's save it as. Can we overwrite the already existing one? Let's rename this to back, I guess, and save this. Yes, I think I fucked up. Yeah, I fucked up. Let's do it again. So we shouldn't rename this. So let's go ahead and rename this to 8120 and save the executable as .new, for example. So it was successfully dumped. So let's now make this .bat debug. Yes, and make this .exe. Now let's run run.bat, and you can see that the new addresses are exactly the same as in IDA. So we disabled the ASLR just like that. Great. So I'm not going ahead to debug this for now. Let's jump into static analysis first. If I attempt to decompile this thing, it will decompile. Oh, okay, it was fast, thank God, but the decompilation looks shit. Like you can see here that this is literally shit. Some random addresses are called, random mode operations. This is pure obfuscation. Okay, and this is actually I think MBA. This is called MBA obfuscation, mixed Boolean arithmetic. if we attempt to deobfuscate, we cannot deobfuscate anymore. So the decompilation ends here in ZAP RAX. So this is sad. This is an added decompilation and added decompilation feature, mechanism, technique, anything. So let's go ahead and find and analyze it statically for starters. So quick enough, we can find some interesting strings. So what's the logic? We need to find which function is responsible for checking if the password is correct or not. So we need to find the handler, the button handler of the OK button, the delete button, and the onNumberClicked button. And these names are exactly here. This is called when we submit the password, this is called when we delete a digit, and this is when a number is clicked, a digit is clicked. Okay, this is some big thing, I don't know what this is. I think, no, I know what this is. This is the metadata of the Qt application. So this is how Qt applications work behind the scenes. Yeah, the meta object system. This is a topic of big discussion. This is, for example, ping and pong. These strings are not simply stored as strings, as normal strings in any application. There is, like .NET, there is a specific section dedicated for the metadata of a Qt application. So let's jump to the beginning of this metadata thing, and this is where these metadata do exist. There are a lot of things going on here, and when I was solving the challenge, actually I spent a lot of time to understand how all of this works. I spent many hours looking at the source code of the Qt framework and try to understand what exactly happens when you run, when you, for example, submit a form. So when any action is performed, any event is performed, a signal is raised, a Qt signal is raised. Okay, I'm not the proper one to explain how the Qt framework works, and that's not the purpose, but you can see that it works with callbacks. So yeah, this image is pretty cool, actually, self-explanatory. So there is somewhere a handler, there is some code somewhere that, let me make a string of this. Okay, there is somewhere a code that says, there is somewhere here, I mean. So this code tells that when, and it sets, there is some code somewhere inside any of these functions, I think, or maybe inside these DLLs, I don't know, I'm not sure about it, but it actually sets one of these methods per action. So for example, there is somewhere a signal being created that says when someone clicks on any of these digits, register this function as the handler for this onNumberClicked thing. So this is the event listener, and there is some code somewhere here that does there is some code here that runs when we click a number or when we delete a number, but I won't do the same as I did while solving the challenge. I won't dive to the source code of Qt. This is a big thing to do. This takes time. So let me use an advanced search engine here, because this is basically the most of the time the things I ask for GPT and stuff is just advanced Google searching. So I have a Qt binary with some strings on number clicked, on submit clicked, and they are handlers for clicking some digits and submitting. Okay, button, tell me, explain me where these functions are registered as handlers for clicking the digits. How Qt handles on clicked stuff. So let's wait for it until it replies, and let's jump to the strings again and try to find the OK button. You remember there was an OK button when we ran the binary, right? So let's run this again. You can see that what happened. Okay, why are there two? Okay, so there is an OK and del and these numbers. So the question is, where in the hell are these strings inside the binary? We cannot find them. And yeah, this is exactly what I mean when I say that this stuff is encoded here or encrypted here. I'm not sure, but this information is simply here, all of this. So let's see how it works, hopefully. So this calls the connect function as shown here. So it registers, it connects the button with the handler. Okay. So you mean that we can just breakpoint to connect? No, this is the wrong connect function. Let's restart. So let's jump into the Qt and find connect. Okay, let's test this out. I'm not sure actually. Let's run connect. Okay, connect is called. Text changed. Okay. So let's inspect the arguments of these functions. Let's check the second argument. This should be a function. Yeah, this, what is this? Widget line control. Thankfully we have symbols inside x64dbg. This is a very good thing, but this does not look interesting actually. Let's skip this. Okay, there is a lot of things going on here. Update, input rejected, update, text changed. I don't know. Too many events going on. This is exhausting. What is the first function that runs when we click a button? It's usually not a clicked handler. Yeah. Yeah, so there is a function behind the scenes that it's called, for example, notify, that this function then jumps to the actual handler. I don't have the source code. I'm reverse engineering for the CPF. Anyway, forget this. Yeah. So let's move ahead. Okay, let's remove this breakpoint. Another connect is called. Come on. Disconnect. Nice. Yeah, actually we don't care about disconnect. What the fuck? Yeah. Same. The rest functions are never called, so this is shit. Let's forget about this. Okay. Anyway, we need to find out what handlers are called when we click a digit. So let's see the main function. The main function, as said, is obfuscated, and you can see that its size verifies that. Its size is actually very large, and if we sort the functions in IDA based on the size, we actually get a lot of very small functions. Sorry, by length. Let's sort by length. So apart from main, there are also these functions. 1, 3, 4. Yeah, these 3, 4, 5, 6, 7, 8, 9, 10, 11 functions that are obfuscated with the same way. This is also obfuscated, and this is not obfuscated. So there are these functions that are obfuscated. Now we can think a bit clever here. This is how I should think when I was solving the challenge, but I did not think of it. So it makes sense that the author wanted to obfuscate the way how the password is actually constructed and how it's verified. So the author wanted to hide the verification process to make it more hard, more difficult to reverse engineer and analyze. So we're pretty sure that all the core logic of the application is obfuscated using this method. So if we go ahead and put a breakpoint to all of these functions and just run the application, we're going to see that this will work. We will eventually hit the right function. But let's show another method here. Let's use API monitor and attach I'm not sure if this will work. Let's see. I'm not sure. So let's attach to this binary. So these are the modules, and let's do some stuff. A lot of things going on. Let's press OK. Sorry, let's delete all of these things and press OK again. No, this is not the right thing to check. Yeah, apparently yeah, we cannot monitor the okay. Can we import our own DLLs here? I think we can. Let's actually go to the file location of this tool. What? Okay. So API internal headers. For example, is there decrypt XML? Don't tell me that I have to make an XML. No way. I'm not going to do this. But you can register your own DLLs here by going to the XML directory and make your own XML file based on all of the API of the DLL you want to monitor. We won't do this here. So we need to find a different way. Yeah, let's open the debugger and let's run the application and press OK and just leave it as is and press pause. What's the call stack? So okay, what happened to the music? Come on, fucking shit. Okay, so what are static meta call? Queue message box warning. Oh, here you are. Look at this. This is pretty interesting. Let's put a breakpoint. Oh yeah. Oh shit, this is spoiled. Fuck. Okay. Where am I? Let's move to this. Actually, let's put a breakpoint to this function. No, what? Wait, no. This is the function. So let's put a breakpoint here and let it run. So let's run this and we hit the breakpoint. This is awesome. So we know that this method call, the queueMessageBox warning thing, came from this function. So this must be the function that displayed the wrong message box thing. So this must be the function that verifies the password. This is a strong indication. And this must be some kind of, I don't know, loader, handler, I don't know. So this must be the function that actually checks the password. So let's go to IDA and jump to this address. Yeah, this is it. What the fuck is this? Okay, let's jump again. Okay, so where does this function belong from? This belongs to this method. Yeah, this is it. Let's jump here. You can see that this is the check password function 20 to be 0. So let's rename this to check password. Let's put a prefix here, or obf, for obfuscated, to know that it's one of these obfuscated functions. So obf check password. You can see that our concerns were verified. We can go ahead and decompile this. Sure. Yeah, of course. The deobfuscation function, the check password function, looks shit. It's obfuscated as fuck. So we cannot see actually the condition that determines whether the password is correct or not. We cannot find this conditional jump. There should be somewhere a jump that jumps to, yeah, this is the wrong password, or yeah, this is the correct password. There should be a conditional jump somewhere. We cannot find this as is because of this jump RAX thing. But this is not a bad thing yet. Let's step back. Actually, we can put a breakpoint. Yeah, so let's put a breakpoint to this function inside the debugger. So let's remove the breakpoint from the DLL. So let's jump here. This is the check password function. Oops, I have already named. But you did not know it. You did not know it. So that's a good thing. So before analyzing the check password function, let's see what function called this function. And this is this function. This is a small one actually. So this is the address. This call RAX function basically is what called the check password function. You can see that this is garbage, so this function does nothing, so this function does nothing too. It's like some mem copies thing. So this is what should matter to us. And what's v9? v9 is the second argument. So let's breakpoint here as well and see what function calls this. Oh, before moving on, let's jump to these strings and see, press X for X references and see that they actually don't have any cross references, and that's because everything happens inside this metadata thing. All the handlers and all this stuff is handled behind the scenes automatically. They happen on the runtime, so it's basically very hard to do this statically. Yeah, so let's jump back and see what function calls this. This function is called by another function, which is this one, and this function is called by this function. And this is the best thing possible that we could find right now. This is the dispatcher function that basically contains three cases, one for each event. There is one event for number click, delete number, and submit password. So this is the handlers, the corresponding handlers for these events, if I remember correctly. Maybe I talk bullshit right now. Maybe we care only about case 1, I don't know, but you can see that this function is assigned as an argument. So this is a callback. This is basically a callback, and I think that it has to do with a more generic meaning of an event. So basically it's a button click after all. So if we put a breakpoint here and press OK, so we click 1, this function is called, and the first argument, so that would be RCX. Yeah, this function, wait, what? Wait, switch A1 RCX. No, RCX is a jump table. Yeah, RCX is the jump table, so we care about RAX. Yeah, care about RAX. We can see that it jumped to case 1. So I think, I'm not sure, I think this should be the handler for any button click. So internally this runs and calls the appropriate method handler based on what button was clicked. Was it the OK button, the delete button, the number button, etc. So most likely, let's debug a bit more actually. Yeah, let's jump into this function, and you can see that there is you can see that QAbstract button on click is called. So this basically, this is the onClick handler for all kind of clicks. Then there should be another handler, another table that contains all the button, all the types of buttons, the OK, the delete, and the number, and their corresponding event listener, their corresponding callback. So this function is called, and this is garbage. Let me check. Wait. Okay. So this is interesting. onClick is called. Do we actually care about this? I think we do. Look, I think. Okay, now I think I remembered something. I think that we jump to the actual handler inside the onClick function. Let's. Okay, I'm gonna. Qt. Let's read a bit of the source code. I could not resist. Qt framework source code. Yep. Q abstract button. Let's search of this. So let's find the class. Oh yeah, this inherits from Q widget. Okay. Oh, what was that? Clicked? Where? Clicked? Oh, Q abstract button clicked. Here you are. Oh, this is an example. Oh, nice. So we have an example. I hadn't found this actually while I was solving the challenge. This is cool. So this is an example. It sets an OK and the cancel button. And you can see that Q abstract button clicked is passed as the second argument to connect. And the actual handler is the fourth argument. Right. So the fourth argument is the actual handler of each button. Accept or reject. This is nice. So let's jump into the DLL call. What's this? Let's look for dynamic calls. Actually, we need for dynamic calls. Oh, wait, what? Is this it? This could be it. Anyway, let's move ahead. Oh shit. Spoils. Fuck. I want to remove all the fucking spoiled. Let's delete all the spoils. Okay. I could rename the database entirely, so anyway. Okay, so where are we now? I got lost. Let's see on the IDA. Okay, we're here. I think that the actual handler is not yet pushed, is not yet clicked. So let's jump here. And look at this. Boom. Now the same method, so the same method, this one, the first time it called the QAbstract button on click, so it called the click method, so it how can I say, it queried, let's say, the table with the registered handlers and said, okay, this button was called, so it returned the appropriate function to be called. So then it jumped back to this place, and now v7 has the actual handler to be called. So this is called twice. The first time it's just the onClick, and the second time with the proper function to be called. So if we jump now to RAX, this is the onNumberClick function. So let's jump to this on IDA, and we will see, of course, that this is obfuscated as well. You can see it from here. So this is 12e50, and 12e50 is one of the obfuscated functions. So let's name it obf onNumberClicked. Okay, so this is onNumberClicked. This is very cool. And again, the compilation fails because jump RAX. So that's cool. Let's run this again. Remove the breakpoint from the yeah. So let's run this again and press delete button. So a breakpoint was hit again. It jumps to the same, to the case 1, jumps inside. So it calls the, it doesn't call the click method. Okay, it didn't call the onClick now. I'm not sure. This is weird. Anyway, we know now the dispatcher. This is a good thing. We know which function is called. We know what function determines which function was called per the button click. So this should be the obf onDeleteClicked. How is it called exactly? onDeleteClicked, yeah. So this is onDeleteClicked, and this is onNumberClicked. Let's jump to this on the debugger and rename this to what was it? Oh yeah, obf onNumberClicked. Nice. So that's a good thing. But again, we can take this address and go to IDA, but of course it will be another obfuscated function, and this is 2f8c0. Here you are, and this is again obfuscated. So let's rename to obf onDeleteClicked. Awesome. So what's left? We need the handler for the OK button. What thing is called on the OK button? So let's run this and yeah, basically remove the breakpoint for now. F9. Let's run this, and before pressing OK, let's re-enable the jump RAX, and we jump again here. Okay, obf check password is called. We have already renamed it. Yeah. So let's rename this from check password to onSubmitClicked to be as close as we can to the original source code. So yeah, there is a lot of stuff going on here, a lot of variables, stack variables. So this is onSubmitClicked. Awesome. We have the 3 handlers for all kinds of buttons. Great. But now, what is actually done when we click a number? This is another story. So, I mean, we could breakpoint to jump RAX and see where we land. So let's breakpoint here and F9. So RAX points to basically the next address. Can you see that? So jump RAX literally jumps to the next address. So this is basically a useless jump function, right? This is very useless. We don't care about this at all. So then some call RAX functions, which again are doing some garbage things. All of these call RAX functions are doing garbage operations. We don't care about this at all. So let's jump to the next jump RAX, and we can see that again it points to the next address. So we're starting to get to see what's going on here. Basically the obfuscation, there has been a jump RAX instruction being injected so that it breaks the decompilation, but the jump is actually useless because it literally moves to the next instruction. So even if we patch this out, it still works, right? So yeah, a lot of indirect calls, many of them. The bad thing is that, okay, interesting. For example, here now a legit function is called. Can you see that? This is a legit function. It looks like a legit function. So it jumps here and does some stuff. I'm not sure what this does. Oh, this reads the digits from the password. Wait, no, it does not. I thought this 0 is anyway. Okay, so what's this RAX thing? Oh, now RAX, for example, no, this is garbage, sorry, never mind. Oops. What about this RAX thing? Of course, I think it will be garbage. Yeah. We can preview the RAX thing, but all of this is garbage. So yeah, not much going on here. Let's go to the next jump racks thing. Oh, what the fuck is this? So let's jump RAX. So still nothing interesting. Look, there is some conditional thing going on here. Wait, what is there in this address? The hell? Get the fuck out. Okay. Fuck. Anyway, let's move on. All of these racks functions are trash. Garbage. Everything is garbage until here. So this jumps to another useless jump. But what is the problem here? The problem is that not all of the calls are useless and not all of the jumps are useless. For example, any conditional jump is performed via jump RAX, but it's done indirectly. So, for example, there is a conditional move on RAX. So, for example, if the password is correct, a specific bit is set, and this determines whether we jump to the correct password or wrong password block of code. Yeah, so we cannot just go ahead and patch all of the jump RAX methods straight away, because we will lose some of the core functionality of the program. So this is where I used some x64dbg Python scripting, and I will immediately show you what I mean. But first, okay, let's begin with the target function, with the check password function, sorry. So let's move to the next step of the challenge. And that's to, wait a minute. Okay. So, get ignored. Yeah, this makes sense. So, for this reason, at the time of the competition, I made this little script a bit different basically, but yeah, this is a core idea. And what this does is that yeah, so there were too many call RAX functions, and I basically wanted to there were too many call RAX functions, and too many of them were literally garbage. So I wanted to find a way to filter out all the methods that all the functions that I should ignore. And look at this. So you saw the pattern before. There were a lot of these move, rax, rcx. We basically want to ignore all of these functions. They are garbage. They are part of the obfuscation of the program. So we want to ignore them. Okay. This actually is interesting. Anyway. So, for example, if you can see these functions here, and what do all of these functions have in common? They are about the same size. I mean, just look at the lengths of the functions. Look how many of them are 8 bytes long. And look at how many of them are 4 bytes long. All of these functions, you can see that all of these functions are trash. So, I think there were some, yeah, these internal calls, we don't care about them. And then obfuscation happens again. All of these functions are to be ignored again. So I made a script, an Python script, that basically iterates over all of the functions of the program. So it iterates over all of the 7,000 functions and checks which function is before this address. So if it's after this address, it means that it's a legit function, don't ignore it. But if it's before this address, let's check this address. So you can see that above this address, all of the functions are to be ignored. So basically, if the address is less than that, then we get, then for example, this is the method, we get the X references, there is no X reference, right? So yeah. Wait, what? Why didn't I ignore everything? Yeah, I'm not sure. Yeah, okay. So we got the X references. I forgot what I did. Oh my god. Anyway, we got the X references of this function. For example, this. So this is empty. It is none. Okay. If it's none, then we simply want to ignore it. But there are some cases that these functions are called from legit other function, so we don't want to ignore it actually entirely. Alright, so if the reference is none, so if there are no X references to these functions, it means that they are called indirectly through call RAX, so we want to ignore them. Yeah, I remember now. So how do I know this is 4 and 8? First of all, we show that from the length, and how this length is derived, we can enable the opcodes here, and you can see that the length is either 3 plus 4 7 plus 1 8. So it's either 8 or 4, simply that. Okay, so let's go ahead and run this script. Quickly we get ignores txt, and it's a large array with all the functions to ignore. This is a good thing. So yeah. Okay. This is what I did during the contest, the competition. But it turned out that before recording this video, I figured out a much better way to deal with this obfuscation method, and I will show you straight away. So what's my idea here is that we want to patch out all the jump RAX functions, instructions that simply jump to the next address. We don't want this jump RAX there because it corrupts our decompilation. So also back when I was solving the challenge, I wanted an automated way to figure out what's the target method, what's the target function being called after, with all call RAX instructions. So for example, if this was, so this for example, this jumps to an ignorable function, so no comment here. But suppose that we run through this, I let the debugger run, and for example this one landed on an address that it's not on these, that it's not one of these, it's not ignored. So I left a comment here like calls for example onSubmitClicked. So I had left a comment like this. Actually, if you see my comments, you can see that there are a lot of calls like that. Okay, so apart from that, let's move on. I will show you what exactly I did at the time of the contest. So basically this is the code that did that. I read ignores txt, and I basically filter out only the jump RAX and call RAX. If the call RAX does not jump to an ignore function, I said a comment to this line saying that mentioning the jump address basically. This helped me a lot to understand what functions are of importance. Okay, but I figured out since the CTF ended, I got some more x64dbg experience, Python scripting experience, so I optimized this and I will show you straight away. So I basically ignored this thing we call RAX entirely and focused on getting a cleaner decompilation. So I focused on patching out all of these useless jump RAX methods. By the way, here you can see a jump RAX and another jump. Anyway, okay, so what I did, so we need a way to figure out the conditional jump that determines whether the password is correct or not. So let's copy and paste our script and let me explain. So let's open up the script in x64dbg Python. So I'm really proud of this actually. This works very good. So I used x86. This is basically a disassembler, exactly like Capstone. Python Capstone disassembler. This is basically disassembler written in Python. But x86, it's a much faster disassembler than Capstone. And kudos to Hexamine for suggesting me this disassembler. I made a lot of use of this and it was indeed very fast. So let me explain. So what I did was that I targeted a function that I wanted to deobfuscate. Suppose, so what's our onSubmitClicked method? This is it. So for example, let's set the OEP here. So this is the function that we want to inspect. So we get its row address, we read the row code, okay, and we dump all of the jump RAX addresses. Okay, this is a pretty simple thing to do. Breakpoint addresses, let's exit. Right, so how can we dump all the jump RAX addresses? We basically run through all of the instructions using the iced disassembler. So we read the row bytes and we iterate through all the instructions. And if we hit a jump RAX instruction, like here, then we append the instruction pointer. So we append this address to the breakpoint addresses, and if a return instruction is found, we just break from the loop. The function is over and we return the breakpoint addresses. So for example, let's run this. Yeah, we basically don't want the x64dbg thing now. Let's run this with UV. What we need iced x86, and let's run the script. File not found. Yeah, of course. It's on the same directory, that's why. Let's run this, and we got all of these jump RAX addresses. So let's print them in hex. Okay, for example, let's take this one and jump to IDA. You will see that it jumps to a jump RAX instruction. This one jumps to another one, etc. and so on and so forth. So for example, this, jumps to another. I don't know why these things are not decompiled, disassembled. And yeah, so basically this returns all the jump RAX functions. Why did I want to do this? Now, yeah, so we have all of the breakpoint addresses. Then I also add another address cast manually. So for example, let's move to the end of this function. So let's take the end address and jump here. So basically this is the last jump RAX, right? So I set a breakpoint to +2. I set the breakpoint to this address, so this address +2, so this lands here. Actually, this is outside of the range. It's a bad thing. Anyway, I think it's not going to be a problem. Yeah, possibly. Yeah, I don't know. Anyway, so what can we do now? We have all the breakpoints. And here is how here is the where the x64dbg scripting begins. So we set a breakpoint to all of these breakpoint addresses. So we set a breakpoint to all of these addresses inside x64dbg. So let me jump to the onSubmitClicked method. So it sets a breakpoint, it automatically sets a breakpoint here, like that. I've already done this. And you get the idea, right? So it automatically sets a breakpoint to all of these jump RAX instructions. Why? And then it literally start from the wait, let me, yeah, this is the start. So it sets a breakpoint and it simulates the F9 click. So it simulates execute till return, or sorry, I think run. Yeah, it simulates run. So it's like I'm running run through the API. This, you can find this here basically. Right? So it simulates run, right? So it starts from the current address, and while the instruction pointer, actually this checks if we are outside of the jump RAX range. So if it reaches to the end, then it runs. So by run, it stops to the next breakpoint, so it stops to the next jump RAX instruction. And it reads the bytes there. If so, this is a bit complicated now. If the current address, so let's move to the, yeah, let's run this. No, we don't want this breakpoint anymore. What the, yeah. So, okay, this is a check password function. So it sets a breakpoint to the jump RAX. Here you are, and it runs. It stops here and it checks if this address has already been patched. If it's already patched, then we want to read RAX. Despite of that, despite being patched, we want to read RAX. If the jump address, if RAX is not simply the next instruction and it's something else, it means that this is a conditional jump. So on jump RAX, if for example the next instruction was not this, for example it was this, or it was for example this, this would be a jump below or equal or a jump greater conditional jump. So we need to unpatch this. We want to revert the patching. Make sense? So we removed this function from the jump, the patched ones, and we assemble back to jump RAX, and we reset the breakpoint there. In other case, we check if it's a jump RAX instruction. In that case, we read RAX again. If the target address, the jump address, is the next instruction, then we patch this out and we assemble with NOP. And we delete the breakpoint there. Make sense? Makes sense. Let me think something. Yeah. Yeah, that's right. And we set a sleep because if we don't set a sleep, actually x64dbg is not intended to be run through scripting, so running 10 instructions per second is not actually recommended. Like, sometimes if I just press F8 and let it run, sometimes it might fail. Not here specifically, but let me show you. I hope I get this. Sometimes when I click F8, there are some problems occurring, and yeah, you saw that I jumped to anti-DLL. That's because I click on instructions very fast. So it's recommended and intended to use a little sleep, just a few milliseconds. So inside the loop at the end, we check if we reach the jump, the last jump RAX function. So we step over 2 times, and hopefully we reach the end. If we reach the end, we just pause there, delete all the breakpoints, and dump the patched functions, the function calls to this file. So let's go ahead and let it run. Of course, wrong password. So let's run this again and let the script run. So for this purpose, I installed x64dbg Python. This is made by Elvis Blue. This is it. So they have released a compiled version of their project here. It's a bit old, 2023. I'm actually already working on this, upgrading this tool to work with Python 3.12, but I experienced some issues, but I will figure them out. It's not a problem. Okay, now about the installation. It's important that this plugin basically utilizes the Python DLL, and it currently works with Python 3.8 and 3.12. So let's let's move on and download this. Let me open this up and see what are the... Yeah, let's copy it to this directory. So let's copy it here and open the... So you can see that, open the contents. You can see that it's compiled for Python 3.8 and 3.10. Okay? Now, this DP32 and DP64 things are just extensions, because x64dbg plugins all end with a DP64 extension. At the end of the day, and most significantly, this is a DLL. This is basically a compiled DLL PE file. So let's decompress this. And for okay, we will work with 3.10. We don't need 3.8. So if, for example, we open PBear and open this up in PBear, we can literally see that it's a PE file, right? This is a classic PE file, nothing less, nothing more. Yeah, and we can see the imports. These are the dependencies of the DLL. Of course, it utilizes some things from the x64 DBG DLLs, and also you can see that it uses the Python DLL. So that's why it's important to have the path of the Python 3 DLL in the path variable. So if we go to the environment variables and we edit the environment variables on the path, and we edit the path variable, sorry, we can see here that we have added 3.10, the directory of 3.10 Python. For example, let's jump to this path. So this is the root directory of Python 3.10, and you can see the DLL that this DLL depends on. So we need to add this path to the path variable. If we don't do this, then the plugin will fail to load. So we have already done this process. If you haven't done this, of course, you just go ahead, copy paste this. You should do this for x32 DBG as well, not only x64 DBG. So you basically copy paste x64 DBG. You copy paste dp64 for x64 DBG and dp32 for x32 DBG. Let's copy paste this one right now. We go to the path of x64 DBG. This is here, x64 plugins, and we just paste it here. Also, I have downloaded the path plugin, this one. They have released a compiled plugin, so we don't have to compile it ourselves. This is a good thing, and hopefully if we close this up and reopen the debugger, it will work as expected, and the plugins will be loaded. You can see here from the logs that the plugin path was loaded, the plugin x64 DBG was loaded, and there were no errors. If we forgot to update the path variable, then there would be an error here, and the DLL would not be loaded. This is how it works, essentially. So let's go ahead and press Alt-7. This is shortcut for run script, and where is it? So let's run this, and it automatically runs. We don't have to do anything. You can see that this is a conditional jump. You see it jumps to the same address again and again. This is where the wrong password string is constructed and will be displayed on the message box later. You can see the wrong password string was constructed. We press OK, and it basically finished. And if we, of course, if we press F9, the binary will continue to run, but the password was already checked. Now, if we go to patch file, we can see all the patches being made, and these are basically 16 patches in total. Yeah, 16 patches. So we can go ahead and patch file. So for example, okay, let's remove the plugin things. We don't care about this right now. We have already downloaded the plugin. So you can see the file being created here. These are all the patched addresses. So for example, if we search for the comma, it should appear 16 times. Yeah, 16 times. One per patch. One per patched function. One per patched instruction, sorry. Okay. So let's go ahead into the debugger and dump this with patched. Right? And 34 patches were patched. Why 34 and not 32? What? Oh, it starts from 0, so it's 17. 17 plus 17, 34. Yeah, makes sense. Okay, so let's close the thing here. Yeah, now I think that I'm thinking that we renamed the functions on the wrong binary, but anyway, no problem. Let's close this up and open the patched version into IDA. We don't really care about the naming. Let's open the patched one and let's jump to this address. We don't want the entire thing to execute, so let's work only on this. We'll basically stop the analysis. Let's cancel for now. Wait, let's cancel this, okay, and decompile. So we will wait a while. Okay, it goes pretty fast. So, and boom, this is the patched function, and all the useless jump RAX instructions were eliminated. So now we have a much more clear view of what happens. This is a loca being called here, right? Yeah, basically this is garbage. Anyway, so let's see where is the wrong password loop. It's either here. Okay. Oh, this looks like this looks like there is a condition here, a less. So this probably is the conditional jump that basically this is a loop that constructs the wrong password string. It decrypts it. It basically decrypts it on the runtime. So yeah, this is already the wrong password path. So let's find the first condition, and this is the first condition. So whether or not we jump to wrong password depends on this variable, which this variable is this check. And this is exactly where we should land. So if this check passes, if this is true, we jump to the correct password path, otherwise to the wrong password. So this is very good news. We found our target value. So somehow something happens to our password and it eventually hashes to this value. So let's write some of our notes here. Target hash. I guess it's a hash. Looks like a hash to me. So let's run the binary again and actually put a breakpoint on this address. So let's put a breakpoint here. And yeah, let's put a breakpoint here. No, here. This is where our hash is passed. So let's run the thing and press OK, and let it run. So you see that the hash, of course, it's wrong. So if we try to write the correct value here, 5796401. So this is the correct, actually the correct hash. So it subtracts the RAX the RCX from RAX, this results to a 0, so the last bit of RAX, the last byte of RAX is set to 1, which is true. And if we run the binary now, we can see that we get the success message. Of course, the flag is garbage because we don't know the actual input that we should enter. But yeah, we found a conditional jump. This is very good. So that's good. We actually want to see how this value is accessed. What's this plus 0x78 offset? I'm not sure about that, but yeah, we need to figure out how this happens, how this works. So let's run it again. Of course, let's enter something. Okay, and so this is the first function being called. And what is this function? It's an allocate function. Wait, is it garbage? Oh, it's the alloca probe. Okay, it's garbage, yeah. So I'm not sure what's the argument being passed here, so let's check. Okay, it looks like, yep. Okay, so let's run this again and inspect the arguments. Yeah, not let it run, and click OK. Fuck, no, wrong password. Let's try again. 0. Let's jump back and breakpoint here and click OK. So this is RCX. This looks like what's our input? It was 111. Okay, so we need to figure out how the hash is computed. We need to figure out how the hash is computed out of the password. This is our task now. Okay, we're only 2 hours long in. That's good. So what's RDX at 0? What's this address? It's code. It's normal code. What? Where is this? Oh, this is on the stack. Oh, this is stack. Okay, we're on the stack. So this is 14 FDB5. This is it. I'm not really sure what this is. Okay, let's see how RCX is used. Let's see. Not really sure actually. So this is a check. RAX. Where is RAX located? Take its value. It takes its value from here. What's this variable? Okay. So let's jump to this instruction. I put a breakpoint here and jump to this instruction and put no. Wait. Following dump. We want here. Oh, it's plus 78. Oh, yeah. So we jump here. Wait, no. Here. Okay. So this is plus 10, plus 20, 30, 40, 50, 60, 70, and plus 8. So this is the hash. Here you are. So let's put a hardware breakpoint here on write and let it run. Oh, this is cool. We actually hit the hardware breakpoint. This is nice. So, okay. That's because when you enter wrong password, the password resets basically. So the hash basically returns to the default value, which is 0. So let's let it run. Nice. So let's type 1. We hit this RAX thing, we don't care. So, oh shit. So we hit a hardware breakpoint, and this is exactly where the hash is written. You can see that this is the hash being written, and it's the result of RCX. But what function writes the hash? Let's jump to this. This is not analyzed yet. Okay. So yeah, this is the function, by the way. Okay, what's the function? It is yeah, what is it? This is it, but what's the base address of this function? We don't know. Okay, you know what? We can use the IDA database that is already analyzed just to locate the function. So what's the address? 16B04. So let's open this up in IDA and jump to this address and find the function. So this is it, 12E50. So this is the function. Nice. So this is basically the function that computes the hash out of our input numbers. So this is most likely the compute hash method, right? Okay. So let's rename this compute hash. Right. So let's copy paste this address, and no, wait, this one, and jump to onNumberClicked. No, what? Why? Wait, onNumberClicked calculates a password? Really? Wait. So, this is much more easier than I thought. Nice. I didn't know that. I was not sure while solving, but okay, onNumberClicked computes the hash of the password. This is good. Okay, so yeah, let's go ahead and breakpoint to onNumberClicked. Let's breakpoint here and let it run. Click 1, we'll get in here. So let's run our script again. Let's remove our hardware breakpoint for now. Remove also this, since we found how the hash is computed, what function computes the hash basically. And what's this one? Oh yeah, we don't care about this anymore. This is the check password and this is the number clicked. Okay, so let's run the x64dbg script again. Of course, change the base address to this. We could pass an argument to the script, I believe, just to make it more clean, but never mind. Let's run this. So let's run this. Yeah, there are some comments left, but please don't mind. Okay, so let's patch the file. 50 patches actually. Nice. You know what? Let's do this. Let's run this, but let's also run this on this function, so we have both in one. So let's also run this. Yeah, this should work. The wrong password is constructed. And the wrong password is, and the wrong password message box is printed, and it stops. Now we have all the patches, so that is 88 patches in total. Let's patch this file and override the patched one. So let's close the patched file and replace it. Yeah, nice. So let's open up IDA again with the patched file. It's good. Oh, patched. Yeah. So let's stop the analysis and jump to the what's the onNumberClicked method. This is it. So let's jump to this. Is this the patched one? Yeah. So let's decompile this. So this function is called when we enter a digit. So let's remove these declarations. As usual, garbage things all over the place. Okay, this is much worse. Actually, this is much worse. And there is a jump out here. I don't know why. Actually, I do know why. Why is there a jump out? So I think this is where we should okay, what is this? This is a conditional check. This looks like, I'm not sure, this looks like a hash computation to me, but you know what, we need to yeah, this is the entire handler. This is too much going on here. Okay, we need a way to isolate some things. So let's debug through this function a bit. Let's jump to this method, onNumberClicked. So let's type 9 and let it run. Basically, Yeah, fuck this comment. Let's run here. RAX is garbage. RAX. There should be some function somewhere that reads our digit from the that reads the digit of the button that was called. I think this is some hardcore obfuscation going on here. 1DB3. What's this? Maybe nothing. Okay, what is this? Again, garbage. What's this? Nothing. This is a useless jump racks being skipped. Nothing. I mean, you know what? We could repeat the same thing with call RAX, like set a breakpoint on call RAX and try to see which functions are do not jump to this ignore list, this ignore range. We could do it instead of manually trying to figure out. This is doable. Oh, I think we missed something here. Oh shit. What is this? Anyway, let's move on. Garbage. And exception. Fuck. We hit an exception. That's because it somehow, after a lot of F8, if you do it too fast, then you usually end up with an exception. Push button, static meta object. Okay, so let's move on and do this with the call instructions. So what are we going to do now? Is that we're going to get we actually are going to we will actually copy paste this, rename it to x64dbg, not patch but comment call RAX, and now we're going to need the ignores list. Why? This will be exactly the same, but instead of jump we will write dump call RAX addresses. So if it's a call RAX, we add a breakpoint to it. So what's the function again? What's the function? This is it. So let's change this to this address, and I think we don't need this right now, but it's okay, we can keep it as is. Oh, we actually don't want all this logic here, it's much simpler now. So we set a breakpoint, this still remains true. We still get a breakpoint, but now we run this, we said okay, and we check, we get the value of RAX. If code equals, so let's make sure this is a jump RAX instruction, FFD0. So if it's an FFD0, then so it's, yeah, if jump address not in ignore list, then we want to set a breakpoint. Yeah, we don't want to patch anything. Yeah, this actually is not required at all. So we need to construct the ignore list first. this is a val open ignores. Is this it? Ignores, yeah. Ignores txt. Read. Is this it? Ignores. Yep. Nice. So if jump address is not in the ignore list, then we want to set a comment. How are we going to set a comment? I need to see my old script. I think that was it. Yeah. Yeah, if it's not, yeah, let's yeah, I think this is pretty much it. Yeah, we want to get the label here if there is a label. So this address calls to that, and we want to set to this a comment calls that. Okay, and if what's the condition? No, we don't want the end. Okay, so step over, and wait, how does this work? What's the last call RAX thing? Yeah, this is the call RAX thing. So we need, okay, I think we don't need this at all. So while the rip is different than the last one, so if we hit the last breakpoint, just skip it. I believe it is good. That's why I did the +2, because to make sure that we are outside of the call RAX range. So +2 means jump here. So if we jump here, there are no more call RAX, so we can simply step out. We could do that. Maybe not. Okay, I won't do it. So let's just run it as is. I think this is pretty much, the code was really made to be reusable. So yeah, nice. So let's jump to onNumberClicked. Yeah, let's rename this actually, because it's misleading. This is onSubmitClicked, right? So let's jump to onNumberClicked and put a breakpoint. So we click 1 and we let the comment run. Will this work? This will work. Yeah, I think it will. Let's keep a look at the logs. It's good that we have an error, because it means that we got inside this if statement. This is very good. So, but of course it's not address, it's current address. So let's run it again. Oh shit. So we need to remove all the call RAX methods. Forget about these comments. Let's remove them. Breakpoints. Oh, we removed everything? Nice. I am fucking stupid. Oh, I did not. Never mind. So let's run this again. onNumberClicked. Okay. So let's type 2 and let it run. Are we okay? Looks good. let's run this. It will take a while, but eventually I will get all the dump here. Okay. Oh fuck, I have already renamed this. This is another function here, but it's not in the ignore list. We could clear the logs for this is ugly. Never mind. It gets the input length again. Okay, interesting. Trans again and again and again. Is this a loop? Okay, how is this clear log? Okay, I need to clear out these logs. How I'm going to do this? I think I had a line here showcasing that. No? No. Shit. I did not. Should we? Okay, let's make a visit array. Okay, so if current address in visited, we actually want to skip all this. Ah, this is over. Breakpoint deleted. Cool. So we have all this dump. I guess we can take this into a notepad file, dump the logs. Okay, and let's make a separate one and do some regex magic. For example, replace anything starting with that, and basically having anything here. Yeah, so let's find this. Great. So find everything, replace everything here with basically nothing. Nice. I do not own this music. Oh. Yeah, this is annoying. We could also do some regex magic here. Fuck! I have some comments. I could skip the labels, fuck. Anyway. Thread exit, we don't care. Sorry about that, I know it's boring, you can skip this. Okay, so fuck these strings, but okay. Let's go ahead and see what we get. So let's jump to this instruction. So this is, oh, perfect. This is the input length. You can see that the comparison with 25, this is basically the length of the password. This is 5 multiplied by 5, 25 bytes in total. So this is a get input length, and that's how I figured it out and renamed it as such. Yeah, so get input length. Let's jump here. This method, it calls this function. So this calls this function, right? Let's jump to this method. Yeah, so this one is, oh, it is not compiled yet. Oh, nice. Oh, nice. Maybe we should go ahead and use these addresses inside the other IDA database. So search this one here. So let's search this address on the IDA database. Oh, nice. So this is sender object. Q object sender. Nice. Good to know. Let's make a comment here specifying the function. Okay, so let's move here. This is the 9050. What is this function? This is some internal Qt stuff. This is it casts, oh, it casts to integer. Yeah, probably casts to integer. Yeah, so this is cast function. Let's also remove the, yeah, like that. So this is a call to the input length again. Really? Okay. Get input length. Does not make any sense, but okay. And never mind. So this is the 88. I don't know what this is. Aha. Okay, this is interesting. So I think this function, so it takes the existing password. This actually appends the digit to the already existing password. So this basically casts to byte. So it takes one, it casts it to a string, and basically does something like I think, I'm not sure, I just think that, for example, it takes 9 and it says 9 plus 2, wait, 9 plus 2 so equals, wait, maybe I'm fucking up something, wait, okay, let me check, please. So this calls this function. Let's okay. Yeah, I think that this literally concatenate digit to password, append digit to password, something like that. Yeah. Fuck my ticks. So what's the next one? So this calls that function, and what is this? Oh, we actually want this address in the patch database, so we'll have the symbols. This is, so it reads the text. I'm confused. Okay. So jump. Maybe we should let it and analyze. It's quite annoying being back and forth into the two databases. So what's this function? Set text. Oh. Okay, I see. So this takes the digit text out from the button and sets the text to the corresponding password box. So the function that writes 1 to this box that you saw, the single box, is this function. So where is it, Thomas? This is it. Yeah, this is it. So this calls that function, and that's a set text. Qline edit set text. Okay, nice. So let's go and move to this one. This calls this function, and this function is QString. Okay, where is it? I think this is the correct one. Okay, I think that's the correct one. Let me check. Yeah. So let's move to the next one. This one is called this. But we already know that this is abstraction text. So what's the address? So take this. Nice. One. I think this is again a Qt function. Yeah, Qt byte array to UTF-8. Oh, interesting. So this converts to a Qt to UTF-8 to UTF-8. My Greeks, sorry. So this is it, and the method is address. You can skip this. I don't know what this is. I should not write the labels, this is my bad. Never mind. So this is again a Qt function. This is a constructor. This looks like an operator. Yeah. Let's move ahead and write this. This is basically this address. Okay. So what the fuck is this? Okay. And I don't know the address of this because I am dumb. So let's jump to this and this. Again, Qt byte array constructor. It's still being analyzed. Jesus, so annoying. This is it. Nice. What about this? We have already defined that. So what's the address of that? 8E0D0. 8E0D0, here you are. This is it. Okay, get input length. Get input length. We don't know the address. What's this? You know what? We could parse this and make a script that automatically sets the comments to IDA so that we don't have to do this on ourselves. But never mind. Okay, so if this, what's this function? This looks useful. Why did it skip it? Let me check. So this is it. Okay, what about this? Okay, so what's this function? Wrong database again. It's annoying. Oh, what? It's another obfuscated function. Oh, nice. Oh, it's cool, isn't it? So get input length. This is this function. But what is this? This is set text. Yeah, text. I'm not sure what. It's pretty weird after all. Oh, the analysis finished. Thank God. Okay, now we can work with one database. So we can close this one. Okay, save, never mind. Okay, so so okay, this is a text. What about, did we, oh my god, this, what I'm doing is not the best but not the worst solution to. It's doable, I can say. What is this? Why are these not handled? Let's move again along and select all of this stuff and press C to analyze. Yes, I think that it should work now. Okay, it's still not analyzed. Nice. Yeah, apparently this is to UTF-8. Okay. Still analyzing. What? Okay, what is this? This is a new function. So let's jump to this, and this is byte cube byte array at oh. Oh, so it first reads the input. It first reads the input length, then it does some things with a hash because another obfuscation function is called. This indicates that since this is a call to an obfuscated function, this means that something about the hash calculation logic is here. So, and then it gets the password, the digit at the corresponding offset. I'm not sure. So this is let's see. Okay, so what's this call? Wait, is this the hash calculation check? What? Okay, interesting. I'm kind of shocked. So yeah, this is where the obf function is called again. So what is this v325? What's this v20? This is it. Okay. By the way, this is as I said, this is MBA obfuscation. This can be significantly optimized to simple arithmetic using simple XOR, simple addition, simple subtraction, and I will show you in a while how this happens. But let's finish up with the renaming and stuff. What is this? Oh. Okay. Anyway, let's jump to this. This is the 8E0C0. And this is, wait, what? XBC4. Yeah, so XBC4, this is it. This is QString. Finally, we have a decompilation. Fucking shit. Okay, so this is the input length. I think this is the next instruction, of course. Get input length, so it computes the length again if it's 25 bytes long. And this one, which jumps to this, and this is the widget is enabled. Is this a conditional thing? Oh, this is a conditional thing. So this checks whether the OK, this checks whether the OK button is enabled or not, something like that. I don't know. Why would it be done here? I don't know. So let's copy paste this, and we have a pretty good head right now. Okay, so we need to dive into this method first of all. Okay. Okay, let's dive into this function and understand how it works. So what are the arguments of this function, first of all? Oh, wait, v300 is the input password length. So this is the password length. Okay, it does some weird operations, and it looks like the input is hashed. The input length is hashed first. The input length is hashed, and then this is the password. Yeah, so this is the current digit clicked. So let's put a breakpoint actually at this address. This is interesting. So let's put a breakpoint here and see what we get. Oh shit, fuck. Anyway, let's press 8 for example and run it. We can see that this is where we get where our click digit is stored. This is interesting. So current digit clicked, this verifies our suspicions. Okay, so it looks like first the input is hashed, and then the current digit that was clicked is hashed again. Okay, and there is some more arithmetic going on here, and okay, there is a lot of things going on here. So let's breakpoint to this call. So let's jump to this function. Shit. All these comments are from the time that I was solving the challenge. So let's type 9 and run it. If we call rex now, where is our input? The heck is this? I don't understand. Oh, this takes wait, what? Did we? Oh, we passed through this. Okay. Wait, so this basically concatenates the digit to our password, and it gets the new input length, right? So this should be 4, right? This should be 4. Yeah, things happen. Okay. So does this really? This is weird. Oh, what?
I'm kinda not sure what is going on honestly now, but this is classic thing. You should expect this. Let's remove the comment, breakpoint, and see what are the arguments. So the arguments to this is the 439. What is this? 9? Oh, this is the click digit. Okay, let's run through this. This looks like okay. Okay. This looks like some hash. This RDX looks like some hash, not gonna lie. Okay, so I think that this computes the hash. Yeah, this is hash computation, I think. This is clearly hash computation. So let's breakpoint that here. So let's breakpoint here, and this is the new the hash, of course, and this is byte array. Okay. Okay. And gets the new input length. Okay, let's see the input length. It should be 4 still, right? It should be 4, yeah. Okay, I'm still not sure. But not gonna lie, there are not really other functions of interest, so we need to dive into this one, right? So we're still on onNumberClicked, if you remember. On onNumberClicked. Is this it? Yeah, this should be it. Is this it? Yeah, now onNumberClicked, yeah. So we need to we need to see how the length is processed inside the hash function. So we need to figure out yeah, what does this function do? I forgot about it. Is this it? No, where? Okay, I think this is it. Yeah, this is it. So let's put a breakpoint here and see what does this function do. So let's run this. 420. Oh shit, I know. Wait, does this... Oh, wait. Okay. Interesting, okay. I understand. set text. Okay, so what this does, I will show you. Let's run it again. So check this out. So we enter 5. Okay, we enter the number 5, and we are at this point. This is the hash, and this is our current password. So what this does is it receives the input length as input. So, and what it does, this is the already existing password, so it's 5 bytes exactly. So it takes the wait, what? I'm still not sure. I thought I know what's going on. Wait. So let's type 9, okay, and run this. So this is the input of the password, the input length. Okay, this is the password length. All right. Can we somehow please? Okay, let's please rename this input length. So it gets the input length and the password. Not password, but to the struct. We need to look here for the password. So okay, this is the pointer. What is this? Oh, it moves to the end of the hash. Anyway, it moves to RCX. Okay, this is the length. So it multiplies the length by 8. Yeah, so 6 multiplied by 8 is 48, and this should return 30. Yeah, 0x30. Okay, this is 48. So the actual value that it's being hashed eventually is, give me a moment, where is it? Where is it? What is this? No, this is multiply length by 8. So this is multiply length by 8. Okay, this makes sense. This is multiplied length. Wait, does this function return? No, it does not. Yeah, it does not return. There is too much stuff going on here, dude. Oh my god. Okay, so let's go here and see the X references. Okay, so this is multiplied length by 8. Let's see. Oh, okay. Shit. Okay, let's run this again. And let me breakpoint here. Basically go here and breakpoint to this, because this is the hash, isn't it? Or is this the hash? Let's put a breakpoint to both and run this. Hardware breakpoint hit. Okay, where are we now? What's this function? Okay, this writes it. This is a checksum. This is the hash. This is the hash. Okay. Let's analyze this function a bit. So let's go to x64dbg, breakpoint here, and run. Oh, fuck this, don't care. And RAM override this. So let's run this. And yeah. What happened? The heck? Okay. Did this work? Wait, what? Yeah, let's restore them and run again. Yeah, let's remove all these city breakpoints. So yeah, forget color RAX and jump to yeah, let's write this number clicked and jump to this function. Okay, now we're here. Now we're correct. Okay, let's I'm looking at the wrong folder. It's 3 hours long. Okay, so let's remove this. I think it's wrong. So patch jump patch RAX. Okay, that was fast. That was really fast. Let's patch this. So let's make it patch 2. And let's open another IDA instance. We could automate the entire process, like dump all of the patch all the jump racks instructions for all the obfuscated functions and set the comments for all of them, but yeah, I did not do that. So what? Let's move to this one now and let's decompile this. Let's stop the analysis, I believe. Oh shit. Yeah, this really looks like a hash function to me. And no, I'm not biased. but look at all this XOR stuff and multiplications and not and or logical ORs. This all looks like a hash to me. So we let the function run and we can see, look at this, this really looks like a hash. So in fact, yeah, RDX returns the hash of the input. Okay, so that's a good thing. We now know that this is ComputeHash function. So this is ComputeHash. So this is ComputeHash. Nice. Okay, now there's a lot going on here. First of all, what's that? No. Okay, that was an important finding. Let's put a breakpoint to the next call of the ob function. I think there was another one here. Yeah. So let's put a breakpoint at this place. You can see that after this call, wait, no, where is the, okay, there's some fuck up with the decompilation here. Let's check this out. So if we no, stop it. Let's undefine this and jump. Okay, this works. So this byte is the problem. We can patch out all of these 4 bytes. Yeah, so here patch program, change byte, and make these 3 bytes to basically nothing. And this is okay. Maybe. Is this okay? Let's undo the patching, please. I don't want to risk being treated with wrong decompilation and disassembly. Let's view the past bytes and undo them. Let's try again. Where the fuck is this function? Hash? No? Are you fucking kidding me? Yeah, this sucks. So we want. Wait. We want. Do we want this? No. Yeah, we want the jump. Yeah, so we want everything apart from this one until byte A2. So we can patch this out. 1, 2, 3, 4 bytes. 4. This is nice, and now we should get a clean decompilation. Okay. Another jump racks. Ah, yeah, of course. We need to open up the patch 2 version and patch here. So we need to jump here and patch program, change byte, change these 4 bytes to nope. And yeah, fix everything up. Can you stop being dumb fuck, please? Fuck this shit. Okay. Let's decompile this and now we should get What's the problem? What? Are you fucking kidding me? Come on. Please. Okay. So, while one. Oh my god. Okay, I think this loop runs only one time though, anyway, if I remember correctly. Anyway. Is anything wrong with the compilation? It shouldn't be. It should be wrong, right? Okay. Okay. Oh, there's something going on. Yeah. Now we return. So we need to change the function's ending address to 14. Yeah. No. What is this? I don't get it, seriously. Oh. Yeah. Ah, okay. Looks like it's... Yeah, there is no error now. Okay. So this is ComputeHash. Okay. This is ComputeHash. This is the final step. But first we need to understand what are the arguments of these hash checks. So there are two calls to this. The length multiplied by 8 is called first. Okay. So the length is hashed first, and this is ComputeHash. Yep. Okay. So we need to jump this call and figure out what happens. So let's jump here. Okay. Now, what are the arguments? I think we need to remove the hardware breakpoint. Let me check something up really quick. Let me check my notes pretty quick. Not the correct file. Wait. You know, it's hard to remember all of this by heart. It's pretty difficult to remember all of this. SiMBA analysis. Is this it? Yeah. Okay. Oof. This is gonna be tough. Okay. So let's put a hardware breakpoint here and on here. 40 hasn't hit it yet. hasn't hit yet. So let's write this, and the hardware breakpoint was hit. In what function? What is the function? Well, P50. This is your number click, I think, right? Yeah. Okay. We need to find the exact arguments of the hash function. This is our goal right now. Okay. So to do that, we need to basically let it run. Hash 5. Okay, so let's remove the breakpoints. Fuck, let's call racks. What's this? Yeah, sure, let's delete everything. Oh yeah, the hash updated. Notice that this function is called even when we deleted a digit, because the hash is updated accordingly. You can see that we removed everything and now zeros are just written. If we enter 1 and let it run, look at this. This is the hash of 1. So yeah. Yeah, so let's delete this and press 2 and see what we get. So let's put the breakpoint back here, and also we want the append. Where is the append? Not ComputeHash, we want the append that multiplies by 8. Yeah, this one. Multiply length by 8. So let's take this and let it run. It takes the length, it's 0, so the result is 0. We're added, and yeah, we need to notice this value. Let's enable this breakpoint now. And what else is interesting? Okay, nothing interesting here. This plus 48 thing is interesting, but it takes part in some interesting shit going on here. So we need a way to figure out what these operations do, because right now it's really obfuscated. We cannot understand what this code does. So the way to do so, it's pretty simple. We can search online for Python MBA deobfuscator. There are a lot of tools out there that you can use, but for me the one that worked and with the easiest way was this one by Denuvo software solution, SiMBA. So it's basically you run simplify. I have already downloaded the SiMBA repo, so let me copy the, here it is, there is dataset. Let me copy paste only simplify and check linear MBA. This is what we need, and the bitwise thing. Let's copy this one as well. So let's make a folder here, not here, here, called SiMBA, and during the contest, I tried to do I tried looking at v311 and see and recursively go back to and recursively see how v310 is computed and v108. For example, v310 depends on it depends on this value. So I hit a dead end. I don't have anything to do with this. But v108 depends on v310. So what I did was trying to recursively go and replace this v108 with this value. So got a big equation that I was hoping I could simplify with MBA, with SiMBA, but it turned out that it was not possible, and I wasted about 13 hours, 14 hours a day trying to make this work. When it clicked, it suddenly clicked to me. I stopped being a dumb fuck and actually thought about a more elegant way. So what if I could just take these things, so let's go here and try to Python simplify. You see? So let's go. Oh shit. Yeah, we need to take this thing and yeah, let's shit. What the hell? What? Yeah. So this is actually the expression to evaluate, right? So if you try to simplify this, you see that eventually this is simply this expression. So this drops down to just, I think this is what is this value? This is this value, okay. Wait, let me check something up pretty quick. Yeah, so we can basically replace and make it even more prettier. So let's go ahead and replace v108 with this, basically this. Yeah, hopefully this works due to the modulo, but I'm pretty sure it will work. Yeah, super cool. Yeah, this works. And this eventually simplifies to just this. While before it was like that. But now that I'm looking at it, I think... Wait. Shit. Specify enable check for level dash z. So we need dash z as well, so that the results are verified. So we need dash z. Z3 is not defined. Oh, UV run with Z3. Will this work? No, Z3. Wait, is it Python install? Pip. No, it's not just the Z3. Z3 solver, yeah. Yeah. It's not equivalent. I'm fucking something up. Wait. So let's go move back. So it reads our input length, okay? Okay. This input length, is this used anywhere? Only to the expression, okay. So again, it reads the input length, it multiplies length by 8. So this is the multiplied length. Then it does some things here. Set text. I'm not sure what this does. Let me see actually what this function does. Pretty quick. Yeah, so what's the set text? Set text. Set expression. Modify. Does history removes the cursor to the end of the line and oh wait. So this is a Qt object. That's why it writes to the 48 offset. This is then a Qt object. This is a Qt object. That's why. Oh, I see. Oh. What is this though? For example, okay, let's find out. So we have this expression that we want to simplify. Okay, so let's move here. Let's make this an one-liner. Okay, so we have v77. Let's replace all occurrences of v77 with this basically, and this is it. This should simplify. Valid string. What was the invalid string again? What? Sorry, what? Oh, fuck, ULL. Yeah, we need to remove ULL, of course. I think this is good. Fuck. UV run with Z3 solver. And yeah, it's not original. But we get this. Maybe we should remove the modulo. So yeah, can we replace the modulo with basically nothing? Yeah, replace just with nothing. So we should use this. So that's the invalid string. Fuck my life. Let's replace this with nothing. Yeah, for some reason it doesn't work. Okay, let's keep it as is, two separate variables. Alright, and let's try doing that way. And verify with the original. It's not equivalent. Oh, there is a mod. There's still mod operation. Okay, let's eliminate mod. Okay. Yeah, this looks weird. I don't know. Maybe we should find another way. I'm starting to get scared here because of how long will it take. I actually expected that I remembered all this by heart. Anyway, I'm not sure what is written here, but let's move on and let's get exactly at where is the fucking here. Okay, this is ComputeHash. So this is the password length. Okay, this is interesting. Let's inspect the argument of ComputeHash at this point. This has to do with the length. So v168 is hashed, which is the password length, and v168 is derived by this expression. But what is this simplified to eventually? Let's analyze this. How the fuck is this possible? Why we don't get the original one? Input expression may be no linear MBA. It looks like it multiplies by 2, something by 2, and I'm not sure. I'm really curious now. Okay, can we put a breakpoint here and inspect the argument? Oh yeah. So let's put a breakpoint here and just debug this, I guess. Yeah, so what's the input? So this is the input. I pressed 2? Yeah, I pressed 2, I remember that. So this is my input. Okay, and this is where the hash should be written. So this now, this should compute the hash of what though? This is the length, the input length. Yeah, okay, anyway. So this returns the hash, but this is not still written. So this returns the hash. This is clear. This works. Wrong fucking database, come on. Let's jump this up again. So yeah, let's decompile again. So this is computed. This computes something related to the hash and the digit we entered. Yeah. So let's, apart from that, let's see how v290 is used. Oh, okay. This is interesting. So this is in password pod len hash. This is used. This is actually multiplied with the other hash. Okay, so let's put a breakpoint here. So what's 296? Okay, let's analyze v2, these two. So v2 is basically this. Okay. And what's v296? Is it something we should care about? What the hell? This looks promising. Let's go ahead and basically throw it into the simplify script. This should work, I think. Jesus fuck. Yeah, forget the left shifting thing. We just care about this. Oh yeah, nice. So this simplifies to basically just this. Fuck yeah, thank God. Okay, so this basically simplifies to just v295 plus this. Okay, so what's this value and what's this value? Okay, so this is some kind of left shifting, and v296, let's go here now. So let's copy paste this and try to analyze this. Oh wait, that's it. Yeah, this verifies. Nice. So let's go ahead and analyze this as well. And this simplifies to simple OR operation. This is awesome. You see how this slowly starts to make sense? Of course, I know there are tools like Triton. I'm aware that there are tools like Triton that handle all of this shit immediately and does all of this stuff automatically, but I'm not familiar with it and I don't intend to learn this new tool right now. I'm not interested in that at all. But all of this process that we're doing right now manually, it's doable through tools. Of course, under the hood, it uses Z3 as well, but there are tools to do this. Okay, it should not be a manual work. Apart from that, also the MBA deobfuscation is doable to deobfuscate with Triton, and also Triton has a symbolic execution engine, so it can trace your digit and the length in which addresses exactly are accessed. So it immediately filters out the trash, basically. Okay, so this basically v204 is basically our current digit that is clicked, ORed, logical ORed with v296. This is awesome. Sorry, wait, no, this is it. No, wait, this. I'm sorry. This is about v203. And what about this? So this should be worm. It should be that. This looks the same. I think this should be the same. Yeah, this is eventually just simple OR operation. So this is it. We can delete this. This is just obfuscation things. And now we can go ahead and deobfuscate also this part. Yeah, so basically we can replace this with, and this with that, and this is just addition. After all this ugly shit is just addition. Okay, this is clear. So it computes v296, which depends on something. Yeah, it's, what does it depend to? It depends on this value. What's 295? This is the input. Oh, input length. Let's name it 0 because there are. So the input length is probably left shifted by 8. We will see. Left shifted input. So left shifted input is added to the current digit clicked. Okay, this makes sense. And this thing is hashed. A modified input affected digit and input, something like that. So yeah, and the result. So we know that it's the current digit clicked plus password length. Probably it's 8, but we can investigate that. It's easy. We can simply left shifted input, we can simply move here and inspect the values. Let's put a breakpoint. So yeah, this is all about RAX. This is 100. Okay, so let's run this again. Let's remove the hardware breakpoint and run this again. So let's put 3 now. Don't care about this. No, I don't care. Now it's 200. So the first time the hash, the string, the input was 1. So left 1, left rotate, left shift by 8. It's so 1 left shift by 8, it's 256. That's 100. And 2, the input 2 left shift by 8, that's 0x 200. This we can verify that by looking at the racks. So it's safe to assume that this is exactly what is hashed. The password length, actually it's input length. The password length is 25. So we are pretty sure that the one thing that is hashed is the input length left shift by 8 and current digit clicked. So that's not true at all. So let's see what else is hashed. This is the first thing that is hashed. What's the other thing? So yeah, the compute hash. Okay. Oh, and pod length hash. So this hash is multiplied to the pod length hash with what is this? The pod length hash is simply the password length, but there's something, it's a bit modified. We need to figure this out. Can we simplify this? Actually, wow. Z3 solver. What's this? Simplify. No, that's it. No simplification. What way if we add no modification? Yeah. Okay. Let's see what exactly is written here. So let's breakpoint at this instruction, run this, and 3. So that's simply 3. It's just 2 bytes. So it's just the input length, dx, so that would be 2 bytes long. Yeah, could be. Let's remove the breakpoint for now. No, let's put a breakpoint here and inspect dx. Yeah, that's 4. I think it's just the it's just the input, actually. Yeah, it's just the input. So it's input length. This makes sense? Makes sense. And what about it? So when they are multiplied, then this hash, okay, so plus 180. Yeah, this is where the final hash is stored. So let's analyze this one with SiMBA. Let's close this. Also this. Okay. So v28. Okay, so we need to replace this value with this and this with this. Then we want to replace v219, which is that. Nice. Let's rename this to h, because it's exactly the same variable, and asterisk is not a valid operator for Z3. So I think we're good to go. And let's simplify this as well. That's Z. And this is simply, wow. Wait, no. Is it real? Wait, I fucked up something, right? Wait, this is not valid. This can't be true. Wait. Let's replace this with H. So this. So let's replace v20 219, right? So this is 8 again, then yeah, so now we can replace this and this and this, and replace that with 8. This looks cool. Oh, this is just addition. So Nice. So this basically adds the already existing hash. So it adds the hash to the what? To the 284. What's 284? It is the product hash product. So this is simply hash product. This is crystal clear. So the final hash is computed like that. So this is how it works. Right? So this is how the checksum is computed. This is cool. Okay, now we have a few options here. First option, of course, is to use Triton, tools like Triton, and figure out how this hash function works and deobfuscate it like that and be able to interact with it locally with a Python script. So re-implement this hash function locally with a Python script, but we're not going to use Triton, as I said earlier. So yeah, the other solution is to emulate this function. So what I mean by that, in here, wait, what's the, yeah, this one. So let's open the obfuscated one at this point. So this is ComputeHash, this is H. One solution is to emulate this entire thing. Since there are no API calls, if there were API calls, then Unicorn would have trouble with that. But at this point we can simply emulate this function entirely and be able to just run it through Unicorn and get the hash. So basically run the entire thing and at the end just read the RDX. No, just read the RCX. Wait, Rax? Oh, wait, what? Is this the hash? Yeah, basically at the end, yeah, basically read the return value, RAX. This should be the hash, the computed hash. But we're going to go the hard way and we're going to do all of this with SiMBA. Okay, so let's go ahead and work backwards. We start from the end and we work backwards. Okay, so what's the, where is the final hash being written? I think it should be this variable, which is written here. Is that it? We need to figure out where the hash is written. Is it? Also, there is no return value. I don't know why. Okay. Anyway, let's start from the end. Let's begin from the end and work our way backwards. So let's start with V95. This looks obfuscated, so let's go ahead and deobfuscate that. So this is plug and play. Actually, I think that let's move this here. So v91 can be replaced with this. Now let's simplify that. So this is essentially v90 plus v94 and that's all. So this is essentially v95, this. Simple as that. Now what else does look interesting? So how is v95? This is the final hash, right? So v95 is what is of interest right now. So v95 is computed from v151, which is this. Okay. So let's take this and replace v81 with this. Hopefully this works. Maybe I think it will not work because there is this multiplication thing. So what's v80? It's this. So this is that, and v79. Nice. I think there are only two variables here. Yeah. So let's go ahead and simplify that. Fuck yeah, this is simple XOR. This is ridiculous. This is simple XOR. Can you believe that? This entire thing is just XOR. Come on. Okay, so load word. What does this load word mean? Oh, it loads only 4 bytes. 4 bytes? Anyway, I'm not sure about that, but this is eventually just XOR. Okay. So, two values are XORed. So, what's v78? Let's compute that. 78 depends on these variables. So there are 1, 2, 3, 4 variables here, but v77, this depends on this. So v77, let's replace this with these variables, and okay, so this is what should matter. Forget the right shift. We need just the offset of the right shifting, so that should be just an addition. So this simply drops down to that. Simple as hell. So this is what v78 looks like. Now what about v136? v136, this should be our input character. So let's go ahead and see what is v137. v137 is this. Is it? So okay, it's not clear about v136 and v70 and v137. Those two are not clear what are they assigned to. So let's work with v147 and v149. So v149 is v147 is v93, which is this value. Okay, so v57, there are only two variables here. Should work out of the box. Yeah, this should work out of the box. So we can simply plug it in, and it does not work, of course. It does not work. Yeah, okay, we can optimize it. This is not a problem. We can basically wait. v147 is v93. v93 depends on that. v73, v74, 99. Anyway, let's move on with v149. Maybe this is easier to figure out. This is v23. So far, let's see what we got so far. So far we got that this is this, and so v78 is literally this. So this is how it works. Most likely. So what's v90 and what's v94? Okay, let's optimize this pretty quickly. This is simple. It's just, this should be simple actually. I don't know. We run with Z3 solver, simplify, and dash Z. It does not work. Yep, it doesn't work. Maybe because we need so hval is this, right? And v95 is literally this, right? We need to figure out these values. We can do so at the end. I think these values are not depending on the input, so they should be static. It looks like they're static. So what about v136? Oh yeah, we cannot deduce this value yet. What about v137 though? We cannot deduce yet. What about v147? This is v93. Yeah, of course. Let's attempt to fix this up. Oh, they are equal. So let's take these. Yeah, I think this should work. So let's take these. Let's take v76 and replace it. Okay. v72 is just this. So let's get rid of it, of this. Now let's replace v75. So let's grab this and replace v75 with 75 with this value. Now v74, let's grab v74 and replace it recursively with this value. Don't need it now. Take v73 and replace it with that. You can see that it significantly becomes very large. So this is what it's optimized to. Oh my god, this doesn't work. You know what? What's the wait, UV run with Z3 solver, simplify and run -x or x. This is what? What? They are equal, right? -x or x, it's not. What? Okay. I see. Okay, let's work with v149 then. Oh, can we? What's the? Okay, what does this simplify to? Okay, what does this simplify to? This should be plug and play. And this is just XOR. So this is just XOR, right? Okay, so what is v149 though? What is it assigned to? This is u23, v23. Okay, what is v23? This is gonna be hell of a thing right now. So v111, this should be v21. So let's replace this with this. Okay, and okay, we keep this as a variable. v147. Oh. So okay, what's v21? Can we get actually an expression for these two only? This is super annoying. Fuck! Fuck! How is this possible, man? Oh. Can this thing be simplified? Okay, what's the... Let's figure out this. So let's go ahead and so this is just XOR again. So this is just XOR. What is that? Okay. No optimization here. What's what V100? What's that? So we know V20 is... Okay, please let me open the other panel because I can't bear with this. It's very annoying. Okay, let's replace V20 with this value. Cool. What's V21? V21 is simply this, and V20 again is the XOR. Replace. Now we have something depending entirely on that. Let's simplify that. Okay, I need to make a script to do it fast. This is very annoying. So from string, this is my string. So what's the simplifier? So let's call this API directly. This is the expr, bit count 64. Use Z3, true. Check linear, no, false. And import what? Import this. I think this is fine. Print, and if this doesn't work, try with 32 bits as well. So let's run this using solver fast.py. Okay. No, wait. I want simplify linear MBA. Oh. This is it. Can I do just from simplify import simplify linear MBA and just work around 0? What? This is just 0? Wait, what is 0? I'm lost. What is 0? All of this thing. So V11. So this thing is just 0? Wow. So what if now we enter this? No, we enter this, but replace this with 0. v22. Wow. So this is basically the same variable. Nice. Okay, so v20, what is v22? v22 is this value, as long as value. It's 21. So let's run this. Oh shit. So this is the expression. This is the entire thing plus 8, right? Yeah. I think IDA already. No, I don't trust this right now. There is a plugin in IDA called Goomba that obfuscates these expressions, but there is a pretty strong suspicion right now that if I run this, it will crash. The entire database will crash, and I don't want this right now, please. Yeah, so this thing consists of v20, which is simply the XOR of these two variables. So this, let's replace that with that. Nice. And there is still v21, which is v21 is this value. Nice. And again v20 is v107, so v110. This is an entire thing that can be simplified to 7 and 7. This is insane. So this value is just plus 8. Seven, sorry. This is just 7. Yeah. So this is 7. So v22 is 7. This is a constant after all. And so v22 is 7. Yeah, v22 equals with v23. Okay, so v23 is 7. Now let's go back. We want to see this value 147, v97, v65. Oh, v147. This is v97, which is, this looks doable. Is this just this value? I think it's not going to work, but let's try. This worked. 32 bits. This is, oh, this is a 32-bit value. It could be. What's this hex value? Oh, this could be. This could be. Anyway, let's skip it for now. And yeah, let's focus on v62. v62 is this. This is this. 96 with 147. But v147 is this. This is mindfuck. Okay, there is a lot of work going on here. It's not that easy. Oh my god. Let's hope and pray. Okay, let's start with V147 again. Or V149. Let's go with V149 best. It works best for us. So V149 is just 7. Nice. Okay. So this is just 7. So V149 is 23 and 23 is just 7. Yeah. This is nice. Let me verify please with my old solution. Solve. No. I'm not really sure this works. Not really sure this is true. Can we please make sure this is indeed 0? It should be 0. Yeah. So let's override 21 with this. Will this work now? It's 0. Yeah, it's literally 0. And please, for the name of God, can we please rename this? So let's grab V21. So this is 0. We can just get rid of that, and yeah, replace 21 with. It lags so much right now. Come on. Replace V21. Only 2 occurrences. Okay, so V20. Let's replace V20 with just their XOR. So their XOR and what? Is there an error? What, the +8? Oh, it's 7. Yeah, it's literally 7. Yeah, okay. V149 is 7. We cannot do something about it. Okay, so let's go ahead with V147. Sorry, V149 is 7. Now let's move to V147. So this is I just saw another interesting thing. There is a multiplication going on here, so let's grab this expression and optimize it. So what's VV64? It depends on these two things. Yeah. So let's go ahead and replace that with this. Run it. Error. Why? Why? Okay, remove the multiplication. Okay, this is just addition. So this is just this operation, right? Yeah, so this looks pretty important. Let's move on with V97. Yeah, which is 62 and 65. Okay, let's move on with 60 with V97. Yeah. So let's see what we get. This is the expression. Okay, so it's V62. Now we can replace this with tac. We can replace this with this. Forget. Let's already copy that and replace like that. So let's go ahead and simplify that and see if it works. Oh yeah, it's just this constant. Let me verify with my notes. No, this is wrong. Anyway, maybe there is a reason for that. Okay, so V60, so what was that? V97. Okay, so V97, where is it? I'm fucking lost. So V97 is, oh my god, V97 is this is it. So V97 is just this value. I want the hex mode. This. So this is okay. So we don't care about the rest. Let's work with that. So what's V62? Let's work on with that. Error. Okay, let's replace V62 with that. Yeah, it's simply this value. Okay, so this is this value. Okay, so let's see what is V98. V98 is the value. Okay, V75 is just this. So let's replace that. V73 is just Yeah, okay, this will be optimized certainly. This is that, and V40 V54 is just this. So let's grab it and fingers crossed it will be simplified. Yeah, this is just XOR. So V151 is just XOR. Well, where did we start? Yeah, so this is XOR. So this kind of makes sense. So look at V63. V63 is the value of this plus 16, but plus 16 is written exactly above and it's this value. Then it adds V97, which is this value. So if you add these values together, you get this constant. So it looks like this constant is multiplied by, what's this constant? This constant is multiplied by V98. Okay, so V98 now. V98 is V151, and V151 is this thing, V52. So it's anyway, okay, we have this. Let's find the other part of the product. So that would be V98. V98 is this, which is that. Okay, this is just XOR operation, so that would be that. So this is the constant multiplied by that. So V52 is, oh, that's great. Okay, I see that V52 depends on V134. Wait, V134. So what's V135 first? Let's compute this. This looks important. Okay, this should be instant. One shot. Ugh. This is ugly. Yeah, we can basically replace V36 with this. We run, and it's just addition. Yeah, so 151 is just addition. So is V100, so V37 plus V38, 0. So this is 1 as well. So this is the value. Wait, I'm confused. Fuck! V134. Okay. V134. Where is this value being assigned? I shouldn't rename them. Yeah, I need the original names. Yeah. Please don't be so fucking annoying. Okay, thank you. So okay, fucking can't. Okay, so V134 is just this. V52, sure. My god, I thought that would be very much more easier. Why? So annoying. Okay, V52 is okay. V51, let's calculate that. Yeah, and V51 is this. This should be a constant, or 4 or something like that. Yeah, it's just addition. Yeah, this is 105 plus this. So I think the offset is static, right? So what is V135? Oh, it's just the sum. Okay. Looks cool. So this can be embedded here. Something is starting to make sense. So what is V37? It's 119. This must be the input. I don't know. What is V38? Oh, it's one. Wait, V37 is V118. What's V38? Oh. Oh, these are two different things, but maybe it's the same error. Okay, let's optimize this as well. Can this be optimized as is? Ah, it sucks. So, what is this offset? No, this sucks. Okay, so what is this offset? This is 100. Okay. What is this value? Let's start with this. Yeah. Oh, I think this is 0. Yeah, this should be 0. Yeah. So V 0. Right. Where is it used? Here. Okay. No, 144. So let's simplify that. This is 0. So what we get? V35. This is V35. Okay. So what is V147 can be replaced with this. Does it work now? This is just addition. Okay. So this is just this value, which I think this is constant as well. This should be constant. So what's V35? V35 is this 0, 0. This is 2. So this is 2. So this is, yeah, this is 2. Nice. So what's V149? It's V23 and V23 is 7. This doesn't make any sense. Oh my fucking god. Let's begin from the start. Let's start from the beginning, okay? Let's start from the beginning. So this is, okay, so what is this? This is XOR. Okay, this is XOR, simple XOR. I don't know what is 149. It's literally not initialized anywhere, but anyway. So what is this big thing? I think I've seen this in the past. It's just 0. So this should just result in 0. So this should be 0. Yeah. This is 0. Okay, nice. Well, 122 0. So this is 46. Okay. I think I have seen this in the past as well. This looks familiar. So V8 is oh, we need, okay, so I guess let's go to V8 and replace that with V7 and go to V7 and replace that with this. And if we run this, we get the value 45, which is value 2D. I see. So this is V9 equals 0x2D. And then there is this calculation. So this is 0. Let's run this. V9. Yeah, so this results in V9, which is 2D. Last 17. So yeah, this is 0, 16. This 16. And v1 is 0, v10 is 16, so this results in v10 is 16. And then what? So v125 is v104, which is 16. Invalid. Wait, am I dumb? v14, v105, v104, this is 16. Yeah, this should be fine, but it's not. Okay, let's I guess let's deobfuscate this. Does this deobfuscate as is? No, it sucks. So 106, I'm not sure about that. So v56, so v16 is okay. So we need to replace v17 with this. Okay, so v16 now is this value. So what's v105? So what's v15? Yeah, v15. And now this. Yeah, looks nice. Error. Oh, there are many variables. Okay, v14, it's unknown. Oh, v104 is wait, v1. Oh, we know this value. This is 16. This is 16. Simply 16. Error. Okay. It's getting 5 hours. If I don't have any progress in 10 minutes, I'm going just to show you the solution. You understand the idea of how it works, okay? I don't want to make this much worse. Okay, so this is v103. Okay, so we certainly know that this value is okay. Let's inspect this value. Oh, wait, and then this value is written. Oh, okay, wait. Then this is 2D. This has to be 2D, right? What? Yeah, what about it? v106. Wait. This is interesting. So v14. Let's replace that. And v14 is 0 to D. Does it work like that or 45? How is this not? Anyway, okay. So yeah, v14. Yeah, v14. So let's grab this. Yeah. So v105 is 16. v14 is 2D, right? What's v15? v15 is what do we get something from that? Okay, we get v15. So this is v15. Nice. That's an interesting finding. So v106 is we don't know it. So what's v16? It's v7. Okay, so let's work with that instead. Wait, this is 16, this is 45. What's the result? 61. Okay, so v15 equals 61. So this is 61 and this is also 61. No, sorry, v16 is as v17 is 61. Okay, and yeah, v17. What's v17? What's the result of this? So it's a constant now, so not 61. We'll get something. No, v106. I'm not sure what this is. I think this is our digit. I think this is our input. Pretty sure this is v16 is our input. Yeah. So do we get something out of this? Since we know. So v16 is 61. No. Oh, v17 is. We know v17. Wait, what is it? Wait, v16 is 61. Error. Anyway, so assume this is 61. Okay, this is v9. Where is it used? Presumably this will eventually work, but so v16 is 61 and v17 is this. So v16 is 61 again, and this should be no. Really? Seriously? What about this? No. Don't understand. Oh shit. I see. We get nothing. The playlist finished. Oh shit. Let's restart this. I'm starting to get tired. This is hard. And I need to debug, I know. So let's breakpoint at this address and see the look at this. It was for my testing. So CL is 3. Yeah, looks like this is always 3. Is this true? What? Let's take a look at the right shifting here. So let's take a look at this address. So this is 4 and this is static. So the final thing is just 4. This is 4. It's just simple as that. So we need to figure out V95, and yeah, we're doing good work so far. Yeah, this is basically this. Okay, what's the shift value here as well? This is 15. Interesting. This is always static? 15, yeah. So this is 15, okay. Yeah, we could do this a bit earlier, I think. Anyway, so this is 15. So the result so far is this. So what's V137? We don't know yet. What's V136? Okay. What's V? Are they equal? Let's see. Let's breakpoint here. What are these verified things? Okay. So let's check for that and this as well. So EAX is this value and is the same. Three. This is breakpoint. Don't care. Yeah. So this is EAX B01. Yeah, it's the same. It's the same number. Yeah. So we can rewrite this as like that. Actually, like that. like that. So what's left is to figure out v136. So basically what value is written here? So basically this value, and this value is this value. So essentially this is v136 like that. XOR v136. So v136 is yeah, v136 is this plus 16 thing, which is this product, and this product is this value. So yeah, let's keep it like that, clean. So what's v52? What's v52? v52 is this thing. What's v134? It's v51. This is v37. We don't know this value. Okay. Let me check something. Yeah, so I don't know, I'm tempted. Anyway, let's inspect the v134. What about it? It's equal to this value, and this value is 38. Okay, it's left shifting. No. Okay, let's view the assembly of this. So let's put a breakpoint there. So this is 51.7e. Yeah, it does not look, it looks input dependent. Yeah, this is input dependent. Okay, so apparently this is input dependent, so we cannot deduce right now what it does. So looks like, okay, let's see what values are XORed here. Is it here? So is it 7? Indeed. No, it's not. Yeah, this is input dependent. Yeah, we'll have verified that. Next. Oh, this is 0? Wait, this is 0? This is not 7? Oh. Let's figure out the shift left here. This is, I think this is not input dependent. Yeah, this is 3. So this is 3. Right? So this is the same as multiplying by 8. So V37 is V118, V118 is the compressed, yeah. Yeah, this is like multiplying by 8. So left shift by 3 is like multiplying by 8 to the 2 to the power of 3. So this should be this, this, right? And yeah, so it should be it. The 18 is something else, I don't know what. What's V117? Maybe they are equal. Let me check. We need to figure out. So let's jump here and here. B05 9. So let's run 6. This is 0. So this is 31. Oh, this is 9. Oh, it's the value that I entered? My digit? Wait. Let's run this again. No, this is always 9. So wait, this is actually 9? Nah. Ow. Ah. So V100. Okay. So V38. Oh. What is this? Left shift. This should be, yeah, let's run this again. Oh, this is 4. So this is 4. No, this. So this one is 4. Okay. Wait, what did I write before? This is just addition. Oh my god. Dude, what the fuck is this? So this is 4. Yeah, this is 4. Nice. Okay, this is cool. So if we say this number is x, then we have so that's v, let's call it x. So that would be v52. Yeah, this is x plus 4, right shift plus x. Okay, and that's v151. Okay. But wait, this is v52 and v52 is the same number. Wait, v52. Oh yeah, this is recursive. So in the end we have this value, and v52 is simply this, right? We don't need the extra parentheses, and v134 is what? It's v37 plus, so this is basically multiplied by 8, right? So v37 is v118. This is basically the digit, something related to the digit. Okay, what's v37? Anyway, we're getting much closer. So let's call it a constant c, for example. Of course, the hash in the end is anyway. Okay, babidi boobidi, we reversed the entire hash function, and somehow I copy paste that from my notes. The hash function is like that. I honestly don't want to continue doing that. You get the idea. There is no reason to keep on doing that. This is very annoying, but you get the entire idea. This is how the hash function is computed. You see, we were pretty close. We found this final thing. All of this was eventually right shifted by 4. This is the last step, if you remember, here. So this is all that, and this constant c. We just had to figure out this part and this part, and that's all. Maybe by debugging we would be able to figure this out, but I did not try, honestly. We can do it. For example, let's see what is sum to the debugger. So dx is 0d36. Yeah, you know what? Okay, let's remove everything. Let's breakpoint here. Let's run this. So dx now is just 1. So dx a2 is our input. That's interesting. So dx is our input, a2. So v146 is our input digit, right? Input digit. Okay. So it looks like from here that our digit is short with 61, and you can understand this from the hash function. It's true. It is short with 61, then this value is then processed further on, and so on and so forth. So now what? Now we have a Python implementation of the hash function. So we are able to replicate the hash calculation offline. So let's jump to the solve.py. So what I did here is, so let me do some tests. Let's define the hash function, and for example, let's compute I think this should be it. Yeah, this is actually the hash function. Yeah. So let's define this compute pod hash. So this applies this formula that we talked about here. So it's the hash plus the hash of 256 multiplied by the length plus the current character multiplied by the dictionary. So yeah, we can basically replace this with h of l, and that would be the same. So let's redefine the function. Clear, please. Okay, let's redefine this. Okay, and compute pod hash. So for example, if we enter one mask 32, yeah, of course it's not defined, sorry about that. So the hash of this is this value. Can we verify that? Let's run the debugger and let it run entirely, and jump to the instruction that not compute hash, sorry, but which one? 2e, yeah, 2e. No, 2 alt insert. Can we jump here? So let's breakpoint to here where, oh shit, let's breakpoint here where the array x contains the hash, and yeah, we verify that we get the same result. Can you see that? 0615 AF F6 7E 71, yeah, we got the same hash. So the question is there really a need to run the hash function for the length? I mean, we can, the possible values of the length are just 25 values, so we can pre-compute them and have them pre-computed them here, and have them pre-computed here. So that's why before I just did it like that. I used the predefined values. So here I have a sanity check to see that this value of course is extracted from the binary by debugging. So now is the hard part, but no, actually this is not the hard part, this is the easy part, where you can use Z3 and find the correct password that results in this hash. So basically, as you can see, the operations are all multiplications, additions and XORs. So this is also, there are a lot of constraints, so the password is large, it's 25 bytes, and it's very difficult that a collision would exist. Okay, so it's very likely that it's most likely that the password will be unique. It's very well constrained password checking mechanism. It's a very well constrained one. So how does this work? We have a lookup table. Let's see what it looks like. So let's define these constants here. So what's the idea behind? So the input is always 256 multiplied by L plus a digit from, and the range of the digit is this. No, until 0 to 39. Okay, so this can be optimized furthermore by saying that it's plus 0x30 plus just the digits 1 through 9. So basically the input of the hash function is simply this. So we reduce the problem to a 4-bit problem. This is significant to do because Z3 is optimized like that, and we are actually looking for solutions for 4-bit solutions. Can you see? We work with 4-bit solutions instead of 8-bit solutions. So if we were to figure out 0x30 until 0x39, this is a single byte, this is 8 bits. But if we just have to figure out the values 1 through 9, this is just 4 bits long. So eventually we have a we can define 4-bit variables. So we create a lookup table to optimize some things. We basically pre-compute all the hashes. So for each possible length and for each possible digit at each position, we calculate the hashes. So eventually this will look like this. What's the, oh yeah, sorry, just like that. And let's print the lookup table, and the lookup table looks like this. So for example, this is 1. So for length 1, there are 25 possible lengths. For length 1, if the digit 1 is at the first place, this is the hash. For length 1, if the digit 2 is at the first place, then the hash is this. For length 1, if the character is 3, then this is the hash, etc., and so on and so forth. We have pre-computed everything. So now here we have created the variables. No, sorry, forget about this. We create the Z3 solver. We define the variables, the 4-bit variables. So this should be length 25 digits long, so 25 4-bit variables. And we constrain them that they should be less or equal to the upper bound, which is 9. Yeah, so each character should be bounded by the value 9. And of course the lower bound is 0. Okay, and we define the hash, the symbolic hash. This is the symbolic Z3 hash. And for each variable, what are we doing? Wait. For each possible variable, so for the first digit, right, we compute the length and we look up the corresponding value. So for example, for the digit at the first place, for length 1, we get the corresponding hash, so that would be it. And we combine all of the results. Yeah, we repeat this. So basically we get all the hashes. So basically we get all the hashes of length 1. This is it. We get all of these 10 hashes. And what are we doing now? This is the most crucial thing that optimizes Z3. We combine them using if. So the first argument is true or false. So is the current character being looked up the same as the digit 1? It's been too long, I can't explain properly, but you can see the solver here. And yeah, actually you can check in Z3 if yeah, can check this out. Yeah, this is if I equals j, the diagonal constraint. Nice link. So if the first condition holds, then x else y. So if the current variable character, so for example the first digit, which is this, for example, if this digit is equal to 0 to the first number, then this is true, so we get this value. Otherwise we define it as just a 0 vector, a 0. So if it's not the correct character at this position, we just add 0 to the final sum. It's like ignoring it. So we append all of these terms, all these results of the if condition into a terms array, and we return the sum. This is a Z3 sum, of course, and it's faster than doing it manually. Then we append this value to the final hash and we compare it to the target which we extracted earlier, which is this. This is the target hash, and by running this solver, let's copy paste. I know I didn't explain it very well, but hopefully you can play with the code and get a grasp of what's happening. So uv run -- with z3 solver solve.py. It will take a while because my PC is a toast fryer, as I've told a lot of times. Yeah. Okay. I promise you it will work. Just hang in there. Just having a question actually. If I copy paste this, does it work inside the binary? No. Okay. So yeah, let's minimize that. Let's minimize everything and just wait for the password. So yeah, until we're waiting, this was my process for the obfuscation. It's not optimal, I know. Some people used Triton and were able to recover the entire thing instantly, probably, but I did not spend time during the contest to solve with Triton, so I wanted to show you my way in this video. If you were if you work on it in a more clever way, you could just debug and have side by side IDA and x64dbg to see what values are exactly XORed and how is the final hash computed. But I decided to go full statically on this, and yeah, this yeah, This took a while actually. So let's wait. Ugh, it takes a while. Oh my god, this takes quite a while. Anyway, believe me that the right password is here. This is the right password, okay? Believe me for now. So let's go ahead and type that. I promise you Z3, if we let it run, it will return this password. So if we click OK now, we hit the debugger and we get the flag like that. Hopefully this runs today, I'm not sure. As I told you, my PC is a toast fryer. Okay, it worked. Yeah, this is the password, you can see that. Target hash, so satisfying, I love it. So yeah, this was pretty much it. I hope you learned something new. I'm not sure, maybe Triton would be the best option. Maybe in the future I'm going to make a video on Triton specifically and showcase it by solving this challenge with it. So all of us will learn and it will be very beneficial. So yeah, this is pretty much it, guys and girls and everything in general. Every viewer, hope you liked it. I'm going to release all of the source code into my GitHub and yeah, feel free to leave a feedback whether you like this kind of content. And we are left with the final challenge of FlareOn, challenge 9. This will be the final boss. But I think it will take much less time than 7 and 8 because most of it was just scripting and I have all the scripts ready. So yeah, we won't spend much time and troubleshooting here. So see you on the next one. Ciao.